1977. A big year. Saturday Night Fever, Star Wars, Apple becomes a company. The first boomboxes take to the streets. Voyager 1 launches on an expedition into the outer solar system. And a small submersible named Alvin begins a dive to the bottom of the Pacific Ocean. February 1977. 250 miles north of the Galapagos Islands. A place where two continental plates are pulling away from each other on the ocean floor. Three men in a miniature sub set off on an expedition that would completely change our view of how extreme life on Earth can be. They were on the hunt for deep-sea hydrothermal vents caused by the rift between those continental plates. Their existence had been predicted for decades, but no one had ever seen them. At a depth of 7,500 feet, their temperature sensors spiked. They had reached volcanically superheated water gushing through the ocean floor. But they also found something that utterly surprised them. Life in extreme abundance, weird and wonderful. How could this underworld support so much life? There is zero sunlight here. Skull-crushing pressures, and yet the Alvin crew have discovered a hidden ecosystem. This was not what they had expected. They were the first to ever set human eyes on this environment, rich and full of life like an underwater rainforest. And then they found the worms. These bizarre creatures are tube worms. They are giants that can grow over 6 feet long. Their bodies are encased in white tubes anchored to the rocks. At their upper end is a spectacular crimson plume. It looks like a tube of lipstick that's been pushed out too far. Or like maybe Mick Jagger's lips? The Alvin team knew that they had come upon a wonderful zoological oddity. What they didn't know was that the worms would reveal an undiscovered ecosystem that we didn't even think was possible. The Alvin crew collects one of the worms and gives it to this man. This is Meredith Jones, the Smithsonian Institution's curator of worms, and as befits his role as chief worm guy, he gives the thing a name, Riftia pachyptala. Jones dissects the worm, and he encounters something that, to us as non-worm people, is really weird. Riftia has no mouth, no gut, no anus. This thing has no way in, no way out. How does it survive if it can't eat, digest, poop? Well, Jones, as a curator of worms, had seen this kind of thing before, gutless worms. Instead of a gut, these worms have an organ called a trophosome. It's brown and spongy and makes up half the creature's length. A trophosome isn't technically a gut, but it does deal with nutrition. But this trophosome was different because there was nothing remotely like food in it. Instead, it was packed with crystals of pure sulfur. Something was going on inside this worm that Jones had never seen before. And that's when Colleen Kavanagh enters the picture.
I was a first-year graduate student at Harvard, taking a course called Nature and Regulation of Marine Ecosystems. And the professors organized so that there were 4 talks on the vents.
Jones came in to give a talk about his worms. It was a long talk.
Amazingly, I was still awake when he mentioned that in this trophosome tissue, it had sulfur crystals in it.
Well, Jones knew that the water spewing from the hydrothermal vents had a high concentration of hydrogen sulfide, a potent toxin to most life forms. So maybe the trophosome wasn't an organ to help feed the worm. Maybe it was a filter, something to help get rid of all the poisonous hydrogen sulfide. And when she heard that,
I immediately jumped up and said, it's clear they must have symbiotic sulfur-oxidizing bacteria inside of their tissues that are feeding the worm.
bacteria?
Bacteria.
And how did Jones react?
He was a little bit dismissive. It was a little bit like, sit down, kid. Ultimately, I was able to get some tissue.
Of the trophosome?
Of the trophosome. So it looks like little pieces of brown tissue. It took a lot of detective work, chemical analyses, DNA stains, scanning electron microscopy, transmission electron microscopy.
Ultimately,
I was right.
so Colleen discovered that trillions of bacteria are living in the trophosome, using the hydrogen sulfide from the vents as an energy source, in a process called chemosynthesis.
Chemosynthesis is a process using chemicals such as hydrogen sulfide as energy sources,
as opposed to photosynthesis, which uses sunlight. Plants do photosynthesis. They need water. They need water and carbon dioxide, which they transform into sugars using the energy in sunlight. But the worms can't do that.
It's dark. We're 2.5 kilometers down up to even deeper. That's, over 1.5 miles deep. So it's complete darkness in the deep sea.
So instead of sunlight, the bacteria ingest and process the sulfides from the vents. In doing so, they excrete sulfur, but they also release energy, which they use to make food for themselves and for the worms. And that's what chemosynthesis is, making food not with solar power, but with chemical power.
So it's apparent from a mouthless and gutless point of view that the worm is benefiting from getting its food from the bacteria. When you're a bacterium inside of the animal, and you've somehow convinced the host to provide you with the sulfide and the oxygen, then you have Easy Street.
So it's good for everyone.
That's right.
Oh, okay, so one thing's not quite tracking with me here. So if Riftia has no mouth, how do the bacteria get into it in the first place?
So we found out that the bacteria were actually getting in through the skin, through the body wall, into the worm.
Wow. Okay, so how do the sulfides get in?
So the hydrogen sulfide goes in via the plume.
So they do have a mouth.
It's more like a lung.
But a lung is for breathing.
That's right. It's breathing oxygen, just like you and I, but it's also effectively breathing hydrogen sulfide, because that's what the bacteria need to produce organic compounds via chemosynthesis.
And that deep red of the plume, it almost looks like blood.
It is blood. They have the blood supply all the way through it. And the blood is carrying the hydrogen sulfide, the oxygen, into the trophosome to the bacteria.
Huh. And this type of chemosynthesis, is it just a worm thing?
Not at all. It's ubiquitous, or it's widespread in nature. Wherever sulfide and oxygen exist, we can look for it, and it's found in many of those places.
Chemosynthesis had been discovered 100 years ago, but after Colleen's discovery, it was established as the basis of this entire new ecosystem, 7,500 feet below the surface. And in fact, chemosynthesis might have been the way the earliest life forms on the planet found a way to survive.
It took kind of getting away from sunlit environments to see that it's really possible and that the whole ecosystem is dependent on the chemicals in this hot water that's coming up. It's like the fountain of life.
Very cool, these vent creatures.
It's actually very warm. Well, they're at hot vents. Sorry.
And I think we'll leave it at that. If you're especially curious about the story behind this episode, check out the link below for an article that dives even deeper into these amazing microbes. And don't forget to follow us on Facebook and subscribe to our channel for more weekly videos. Thanks for watching.